Bismillahirrahmanirrahim. Assalamu alaikum viewers and welcome to my channel once again. And today we are going to handle the part 2 of our previous video that deals with the examples of beta function and beta integral. So over here you can see that the very first example that we are going to handle here, you can see that at this side we are having a definite integral involving an integrand which is expressed as the product of trigonometric functions sine and cosine, and this integral, this definite integral, is expressed by means of gamma functions. So the question might comes in mind that I cannot see any such beta function involvement here. So why this question is included in the examples of beta function? So actually your beta integral or beta function is contributing here in establishing the relationship between this definite integral involving trigonometric functions to the gamma functions. Alright, so we are going to take the help of beta function in order to maintain this relationship. Okay, so let's have a look and let's start. So this is the definition of this beta integral. We have studied this already. And one thing more that we have studied in the previous in one of the previous videos in which we established the relationship between beta and gamma function, we proved that beta function is equal to the gamma functions in this order. Okay, we have proved this thing. You can view in one of the previous videos of mine. Okay, so now we are going to pick up this integral. Okay, and I'm going to perform some substitution here. Okay, so I'm going to assume that my x is equals to sine square theta. All right, now I'm going to differentiate both sides with respect to my x. Okay, when I differentiate both sides with respect to my x, like this, so this thing is going to give me 1. All right, and this is actually what this is going to behave as the format of xn. Okay, I can write my sine square theta sine theta whole square. That makes sense, and it is permissible. So I'm going to apply here the formula of derivative of xn, which is n times x power n minus 1. So suppose that this is your x and this is your n, so it is n x power n minus 1. It gives me power 1 here, so I'm not writing that thing. And then I'm going to apply my chain rule on this sine theta. Okay, and it's going to give me cos theta. All right, then I'm going to apply the chain rule on this angle theta, and nothing is going to give me, so d theta by dx will be written as it is. I'm sorry, it's x. Okay, this is my x. It's just messed up a little bit, but I hope you can understand that this is d of x. So this dx will move over here, so this thing comes to this thing is going to tell me that my dx is equals to 2 sine theta cos theta d theta. All right, so let me do over here, let's make a proper column. Okay, so this thing tells that your dx is equal to 2 sine theta cos theta d theta. All right, we have just handled this thing. And one thing more that I should write over here, though I can manage while performing the integral substitution at this step, but I can do this thing over here as well, that 1 minus x is equals to 1 minus x was your sine square theta, and this is equals to your cos square theta according to your major trigonometric relationships. So at the place of your 1 minus x over here, you can substitute cos square theta, and also you can do it directly once you are performing the integration out there. So this is your choice. Okay, now let us transform the limit values, the integral limit values over here. So if your x is 0, then what is going to be the value of your theta? All right, so if x is 0, then what is going to happen? What is the value of your theta over here? So you see, if your x is 0, let me do some rough work here. Let me use this definition of your x. If your x is 0, and this is your sine square theta, you take square root at both sides, you come to know that your sine theta is 0. Then you take sine inverse at both sides. So once you take sine inverse at both sides, then you see the inverse function is going to cancel out the effect of the sine, and this theta is going to left, and sine inverse 0 is nothing but 0 itself, okay? Because you know the sine 0 is 0, sine inverse is 0 as well. So that's it. So over here you just write 0, okay? In the same way, if your x is 1, then what will be the value of your theta? If your x is 1, then what will be your theta value over here? So use this definition once again. At the place of your x, you put your 1. So 1 is equals to sine square theta. All right, you take the square root at both sides. The sine theta is equal to plus minus 1, but over here we are just going to focus on the positive value because we are talking about the upper limit. So you just take 1, and then you take sine inverse at both sides. So I'm writing here directly. Sine inverse of 1 give you pi by 2. Okay, so if your x is 1, then theta is going to be your pi by 2. Okay, so now the limits are well defined. Limits have been transformed with respect to your new variable theta. Okay, all these things have been transformed. It's all done. Now we are going to perform the substitution here. Okay, so you see your beta Lm, beta function of Lm, which was equal to this. Oh, the weather is getting cloudy. We're expecting rain here. It's good after a long hot summer. Okay, so now we are going to shift. We are going to change the limits as we have done in the beginning over here. So at the place, if your x is 0, then theta is also 0. If your x is 1, then theta is going to be your pi by 2. It's going to be your pi by 2. Okay, at the place of your x, you're putting your sine squared theta. Sine square theta whole power L minus 1. At the place of your 1 minus x, you're putting cos square theta power m minus 2. It's cos square theta power m minus 1. At the place of your dx, you're putting this 2 sine theta cos theta d theta. 2 sine theta cos theta d theta. That's it. It's done. Now we are going to help out this thing. This 2 is a constant value going to be written outside the integral or before the integral in the next step. Okay, so so now you can see that if I multiply my L minus 1, because the powers are overlapping, so I'm going to multiply this 2 with my L minus 1. So I'm having here 2 times L minus 1. Okay, and this is also your sine theta getting multiplied with this, so it is having power 1 here, so you just add power 1 here, because when two similar bases are getting multiplied, you add up the powers, you know that. And same process you're going to apply over here in at the place of cosine. here the powers are overlapping, so you are going to multiply, and over here, I'm sorry, I forgot to write my theta here. So this is your theta. Okay. And this cos theta is having power 1. I'm going to add 1 over here. That's it. Okay. So you see now 2L minus 2 plus 1 give you 2L plus 1. Okay. So let's do it on the next page. Okay. So over here, I'm going to help out this thing. It's going to be my sine theta whole power. It is going to be 2L minus 2 plus 1. 2L minus 2 plus 1. And I'm going to do the same thing at the place of cosine as well. It's going to be 2m minus 2 plus 1. It's 2m minus 2 plus 1 d theta. Okay. So now what I'm having here is sine theta whole power 2L minus 1, okay, and cosine theta power 2m minus 1 d theta. Okay, and you have studied over here that your beta function of Lm is having gamma relationship of this type. So how about if I replace this beta of Lm by means of this gamma relationship, gamma function relationship? Okay, so how about if I replace this thing with this? Okay, it is permissible, as we have proved this thing already in the previous videos. So let's take the help of it. So let me write down that this integral is equal to my gamma function of Lm upon gamma function of L plus m. That's it. Okay, that's it. So I'm going to shift this 2 over here at this place. And this 2 has gone over here, so I'm going to write it over here. Okay, now what I have to do, I have to bring P at this place, Q at this place, so I'm going to do some letting work. So I will let 2L minus 1 is equal to P, and 2m minus 1 is equal to Q as per your question requirement. As you can see, this was the requirement. So at the place of these powers that we were having here, I'm going to replace them by my P and Q in order to get the form of the question. Okay, so once if this thing is equal to P and this thing is equal to Q, then what is the value of my L and M? So this thing tells me that my L will be equal to P plus 1 upon 2. Okay, that's a common, it's a preliminary maths. I don't think so it needs any elaboration. That's an understood thing. Okay, so at the place of your L and M, you're going to put these values and you are done now. So let's do it as swift as we can. Get the final form. That's what we have done. And now the only thing that is left is that we have to take out the LCM in the denominator gamma function, and then we are going to get the required question form. Okay, so we are going to take out the LCM now, and then we are done. Let us make a column. Sufficient space we are having. But this is the last step. So you see that we just got the relationship of this definite integral involving trigonometric functions in the integrand with the gamma functions by means of beta functions. The beta function is actually behaving as a parametric function here. It is performing parametrization here. Okay, it is serving as a third party. Okay, so now once when you just do the take out the LCM, so this thing is giving me p plus 1 upon 2 gamma function of q plus 1 upon 2 upon 2 times gamma function of p plus q plus 2 upon 2. That's it. So this was the required form. This was the required form that we were discussing in the previous in the question in the beginning of the lecture that we showed that I showed you the question. It was exactly of this type, and this thing has been brought by the help of gamma function. Okay, so gamma function is playing a chief role over here in establishing the relationship with the the beta function is playing a chief role here in establishing the relationship between gamma function and this definite integral. So this is done. Now let's move ahead to another example, which is also the property of your gamma function, and we are going to do it with the help of the beta function. So let's see that example. Okay, so here you go, another example. You have to find out the value of the gamma function of half, which is equals to under root pi. We know that it is under root pi. So how it has been brought to under root pi? What is the process? So over here, the previous example that we have done, we are going to take the help of that, and we are going to pick up that relationship of definite integral, this one, to the gamma function. And this is something that we did with the help of the beta function involvement. We proved this relationship, and now we are going to take the help of this relationship in order to get the value of gamma function of half. So if I just assume that if your p and q both values are 0, okay, then let us substitute the values of p and q, which is 0, in this relationship. What we are going to get? The sine theta whole power 0, cos theta whole power 0, okay, and over here at the place of p we are having 0, so just half is left. Gamma function at the place of q I'm having 0, so over here as well the half is left. Okay, 2 times gamma function, p and q both are 0, so 2 upon 2 I'm having just 1. Okay, so what I'm having here is the square of the gamma function of my half upon 2 times gamma function of 1, and you know that gamma function of 1 is 1, and we have done this thing in the part 1 of our gamma integral. You can see that video in my record. Okay, so no matter what the base you're having, if you're having power 0, then this thing will turn into 1. So this thing is also 1, and this cosine theta power 0 is also 1. So you're having 1 in the integrand now, okay? Upon 2. And you can also write now, because this is 1, gamma function of 1 is 1. So as you're having this 2 in the denominator, so you can write this thing in this way as well. Okay, that's it. So now when you integrate the unit integrand, you are having this variable back. You apply the limits. Okay, alright, so now once when you apply the limit, you apply the upper limit minus lower limit. Okay, so it is 1 upon 2 the square of the gamma function, half. That's it. So over here I'm just having pi by 2 left, and over here I'm having this thing, half times the square of gamma function of half. half times square of gamma function of half. This 2 and this 2 gets cancelled. Now I'm simply having this. I take the square root at both sides. So I'm taking square root, just the gamma function of half, it is equals to your under root pi. So that's how the major property of gamma function has been understood, has been derived, has been evaluated, have been proved by means of your beta function relationship. Okay, the relationship that has been so maintained by means of the beta function, that relationship is helping you in determining the value of your gamma function of half, which is the very chief characteristic and very chief property of your gamma functions once when you apply the gamma integration. So that's it. Let's move ahead and see one more example, and then we are going to end up this video. Okay, so here you go, the last example of this video. You are having a very typical looking integrand here, and the limits are also quite different from that of the gamma function. So first of all, what we do, we have to prove this integral equal to this. That's what our objective is. What we have to do now, we are going to help out the integrand here. So how about, and you are having these two factors are behaving as a radicand of a radical of index 4. Okay, so if I just separate these two factors in two radicals of index 4, they are going to be written like this. Okay, so I've just split up the radicand in two separate radicals of index 4, and I'm not interested in writing the radicand in under the radical, so I've just removed this notation and I replace it with the power of the radical 1 upon 4. So this is it. Now you see, this is not according to the format of your beta integral at all. You have to transform it into the required format, as well as you have to convert the integral limits also in 0 and 1 instead of 3 and 4, 3 and 7. So what substitution you should apply at the place of your x so that you can get the desired format of your beta function? So I just thought, what should I do? So a clue just has just arrived in my mind, and I just decide to substitute my x by 40 plus 3. Alright, if I take this thing, then I can get my desired integral limits of the beta function. So once when I differentiate both sides with respect to my x, when I differentiate both sides with respect to my x, I just got 1 here. Okay, so dx is equal to 4 times my dt. This is it. At the place of my dx, I'm going to write down this. At the place of my x, I'm going to put this. Now let us check the limits as well. So if my x is 3, then my t will be equal to what? Okay, that's the story. So use this definition. If my x is 3 here, then what will be the value of my t? This 3 will go over here. I'm having this. 40 is 0. So t is therefore 0. So my t will be 0 here. That's how we just transform the integral limits. In the same way, if your x is 7, then what will be the value of your t? So if my x is 7, then what will be the value of my t? So use the same definition, put the value of your x over here, which is 7. So 40 is equals to 7 minus 3, which is 4. So t is equals to 4 upon 4 and it is 1. So my t is 1 here. Okay, so you see the limits have been just helped out, and now we are going to sort out this integral. Let's do it. So these are the limits. If x is 3, then t is 0. If x is 7, then t is 1. At the place of my x, I'm going to put down my 4t plus 3. And at the place of my dx, I'm going to write down my 4 dt. This 4 will be written outside the integral in the next step. Okay. And over here, minus 3 plus 3 cancelled. I'm having 4t power 1 by 4. And over here, I'm having 4 minus 4t power 1 by 4 dt. Okay. You can see that I'm having this power is going to be applied not only on 4 but on t as well. And if I take my 4 common outside, then once when it is taken outside the bracket, I have to use this power. I have to apply this power on this 4 as well. So I'm having something like this. I'm going to write these constant values outside the integral. And now just this is left. Okay. Same base is getting multiplied. I simply add up the powers. Okay, and I have to write down, I have to adjust this limit. What should be subtracted? From which fraction when I subtract 1, I should get 1 upon 4. You can do it in your mind, either you can do it numerically. So 5 upon 4 is that fraction. Once when we subtract 1 from it, we get 1 upon 4. Okay, so now you can see that this format is exactly according to the integrand of your beta integral. So I can now, it is now exactly according to the definition of your beta function. So I can now write this beta integral with respect to my beta function. This is my L, this is my M, so beta of L and M. This is it. And now I have to help out this thing. So I'm just writing this 4 as 2 square, and this on, after taking out the LCM, it becomes this. It becomes 6 upon 4. So now simplify. I'm having 2 cube here, which is equal to your 8. Okay, and this is now, I'm going to use the relationship between my beta function and gamma function, which was this. So now I'm going to use the gamma relationship here. Okay, so it is now these are the two gamma functions, is quite similar, so I can write them as in a square form, and this is 2 times my 5 by 4. Okay, that's it. So now 2 and 4 will get cancelled. I'm having 5 by 2, gamma function of 5 by 2 in the denominator. I have to bring this form. What to do now? This is the gamma function. You have studied the property of the gamma function, that the gamma function can be expressed as n minus 1 times, gamma function of n is equals to n minus 1 times gamma function of n minus 1. You have studied this property in the gamma integral part 1 video. So we are going to use this thing. So if your n is 5 by 4, then n minus 1 will be equals to 1 upon 4 and taking out the LCM. Okay, so I can write it like this. Gamma function of n is n minus 1 times gamma function of n minus 1 whole square. And same story you're going to apply over here in the denominator as well. So if your n is 5 by 2, then n minus 1 will be equals to 5 by 2 minus 1, which is 3 by 2. Okay, so gamma function of n is 3 minus 1 times gamma function of 3 minus 1. That's it. Now you see you have to apply one more step. 3 by 2. If 3 by 2 is your n, then n minus 1 will be equal to half on taking the LCM. Okay. Over here, once you are applying the square, not only on this but on this as well, so it becomes 1 upon 16, 1 upon 4 times 1 upon 4 gamma function whole square. And this gamma function n can be written as n minus 1 times gamma function of n minus 1. Okay, so now you see gamma function of half is under root pi. This and this gets cancelled, give you 2. Okay, so 1 upon 2 gamma function 1 upon 4 square upon 3 upon 2 dot 1 upon 2 under root pi. This 1 upon 2, this 1 upon 2 gets cancelled. This 2 will be inverted, goes in the numerator. And you're having this 3 under root pi left. And this is the answer that we were asking to bring. Okay, so we just did that and it's done. So I hope you have understood. That's all for today. And if you find this video helpful and you feel that the examples are very much clear to you and you are satisfied, so I humbly request you to subscribe my channel, hit on the like and share this video as much as you can. So take good care of yourself. Allah Hafiz.